Welcome to Advanced Reverse Engineering. There's homework, and the homework is to identify all the basic blocks in a piece of code. I'll give you some code. Your job is to find main. If you can't find main, if there's not a main, then you'll start from the entry point. So to be clear here, you're going to use the heuristic we already developed. If that works, start there. If it doesn't work, start at the program's entry point. Okay, pretty simple, I think. So now you're going to do two passes. In the first pass, I want you to identify block leaders. In the second pass, I want you to actually print out basic blocks. Now, why can't you print the basic blocks in pass one? Because you don't know what all the leaders are yet, right? And so you might overprint, right? You know, you stop a basic block when you encounter a block leader. And since you don't know where those are, you can't print the basic block. You can't print them until you've got all of the leaders. Okay, now, I also want you to do this by systematically exploring the program. So when I say start at main, here's what I mean. Get the basic block for main, or for the entry point. Process that basic block and find any leaders in that basic block. Notice I keep saying basic block, and I just said, well, you can't know where it ends. That's fine. Process just that block and look for leaders. Okay, you can know where control transfers out of that block, and that's going to tell you where the other leaders are. So to be clear, don't just swipe through the entire text section looking for leaders, because you'll get the wrong answer. I want you to process a block and find leaders, and then for each of the leaders that you find, I want you to go and process that block and look for leaders there. When you're done, you'll have a complete set of basic block leaders, and that will let you then go and print the correct basic block for each one. I hope that's pretty clear. A basic block ends when you encounter return from interrupt, halt, conditional branch, unconditional branch, loop, or conditional loop. And you discover a block leader when you encounter a conditional branch, a jump, a call, or a loop. Loop is left out of this. Unfortunate typo in the slide. But if you encounter a conditional loop, then that also, or just a plain loop, that also gives you basic block leaders. Okay, so there you go. There's an example of running this algorithm in the course slides. Oops, what has happened to, there we go. Temporarily had a snafu with my network connection. Let's talk about satisfiability. So let's first talk about decidability once more. I think that's going to be relevant. My favorite example is the hailstone numbers. Here are the hailstone numbers. Our good old friend, the hailstone numbers. If n is odd, multiply it by 3 and add 1. If it's even, divide by 2. Sequence terminates when it hits 1. And the conjecture is that every sequence for any positive integer n terminates at 1. Now, it says the Collat's conjecture, not the Collat's theorem, but the conjecture. That's because it hasn't been proven, and we don't know. We just don't know the answer to that. Okay, so over on the right-hand side is a program that will print out the hailstone numbers. And you can see at the bottom, I've tried it for 23, and you can see they go up and down and up and down, and eventually 23 reaches 1. The length of that path is not necessarily related to the size of the number. 23 took several steps to get there. 32 would only take 6 because it's 2 to the 6th. So there you go. So here, over on the right-hand side, we have some C code that also checks the hailstone numbers. Up at the top, you can see we have void hailstone. I give it a 64-bit value, unsigned value. If it's 1, while it's not 1, I check to see if it's even or odd. If it's odd, multiply by 3 and add 1. If it's even, divide by 2. And so I don't return anything from this. The trick behind this piece of code is this code only halts if that value, if the input value also halts, if it reaches 1. Now we don't know if everything reaches 1. It's unknown if the Collatz conjecture is true. So what about that code? So, and let's ask some other interesting questions here. Value is not copied back. Value is passed into this function not by reference but by value, which means that the compiler might look at this and say, you know what, this doesn't do anything interesting, I'm going to get rid of it. And so the compiler is effectively saying it always terminates. Does it? Right? Does it? Well, do we know? And another interesting question is, right, this only terminates if value does eventually reach 1. And so I have to ask you the weird question, is the termination of that hailstone function decidable? Is it decidable, given that we don't know if all integers terminate? Is it decidable? And weirdly, it turns out, we can check to see how long it takes. So I ran this on my machine, the little framework laptop. Not super beefy, but here's some times. I tried it for 8-bit values, all 8-bit values. Took a less than 1,000th of a second. I tried it for all 16-bit values. It took about 1/100th of a second. I tried it for all 32-bit values. It took 15 minutes to do that. I actually tried it for 24 bits, and that took a while. I did not try it for 48 bits, but what I did do was, so I tried it for 4, 8, 12, 16, 20, 24. I tried it for every iteration of 4 bits. And it turns out that if you take the log of that and fit it, then you can estimate how long it will take for more bits. And for 48 bits, I estimated it would take about 4.5 years. And for 64 bits, I estimated it would take about 110 million years. Wow, okay, so I'm not going to do those to see for obvious reasons. So we can't try all 64-bit values, can we? Not with this. Now, what if I ran it on a big machine and I ran 1 million of them in parallel? Okay, assuming they all take about the same amount of time, which they don't, right? Because you can imagine as numbers get bigger, they can potentially take longer to converge. But the time a number takes to converge is related to how big it is. But smaller numbers take a while to converge too. So they're going to take longer and longer to converge as you get higher and higher. Even when they're powers of 2, they're going to take a while, several steps to converge. So I don't know if that number is accurate or reasonable, but there it is. Now, if I ran it, like I said, if I ran it on a giant machine, let's say there's 1 million nodes, and so I can factor this and I would run 1 million of them in parallel. It's still going to take me like 110 years. It's impractical. So, and what if some of them don't terminate? What do? Just keep waiting? So, geez, I can't try them all. We don't know if the conjecture is true. What do I do here? Well, it turns out this is decidable. It's decidable because it's basically a very large finite state machine. In that little hailstone loop, I can only have 64-bit values, and there's a finite number of them. I can try them all. And then the question becomes, well, what if it doesn't terminate? Well, there's only a finite number of values that it can take on. And so by the pigeonhole principle, I have to eventually revisit a prior value. At that point, I know it doesn't terminate. So it turns out it is, in fact, decidable. So, and there are ways to improve the search time and all of that. But the growth tends to remain exponential. So it turns out this is decidable. We don't know if the thing is true. I mean, everything that can go wrong is going wrong here. It's still decidable. Now, why is this relevant? Well, again, I want to keep emphasizing to you that most things about most programs are decidable. Okay? It's hard to write a program whose termination is literally undecidable and not just hard to figure out. So you should give it a try. See if you can think of how you would write a program whose termination is undecidable. So even in this most extreme case, it turns out it's decidable. So let's go back and revisit program slicing and termination with all that stuff in the back of our head. Here's a short program, and we might ask the question, under what conditions does it terminate? Does it always terminate? Does it loop forever sometimes? What does it do? So if we take a look at the code, we'll see we define some stuff up front. We define start, stride, and end to be certain values. And then we start, and we zero out EAX. I set RBX equal to the start value, and then I go into a loop. And I add the stride to RBX, so I add 7 to it. I increment RAX. I compare RBX to the end, to 701, and if it's not equal, I go back up to the loop. So I just add 7 until I hit 701, and then I stop, and along the way I just count. And then I put the total number of steps into RDI, and I return. There you go. Well, how could I figure this out? So there's some stuff going on in there we don't need to know. So let's construct a slice, and we're going to construct what's called the control slice. So we're going to pick a point in the program and a value and discard anything that doesn't affect the values at that point. And if we want to just focus on the loop, what should we pick as our condition for our slice, slicing criteria? We're going to pick program termination. And so program termination is going to happen when we don't take that jump not equal branch. We don't take that branch. In other words, we fall through it and terminate the program. So that gives us something to slice on, right? Jump not equal means the zero flag has to be set, right? Because the zero flag is not set, then we're not equal, and we go back to the top. So it must be set so we fall through. So that means we care about ZF. We go back one and we ask, does that previous instruction modify ZF? And it does. It's a compare. Okay, what are the, so we know that ZF is being set. It's an L value, so we remove it from the set of things we care about. We put in the set of things that it depends on. In this case, it's just RBX. And so we go back another line. We're incrementing RAX. It's not modifying anything we care about, so we throw it away. We go back another line, and now we're adding to RBX. RBX is the only thing in the set of things we care about. It is an L value, so we take it out. But it's also an R value, so we put it right back in. We go back another one, and we might go back to the loop again, but here we'll just move up to the move. We're setting RBX equal to start. RBX is an L value, so we take it out of the set. It's not an R value. There's no other R value, so we don't put anything in the set. Set's empty, we're done. Always terminate when your char set is empty. Just immediately stop. And so we now have what we'll call the control slice, and that's it right there. We've reduced the problem down to a lot fewer instructions. So we set RBX to the start, we add the stride, we check to see if we're at the end, and we loop if we're not. There we go. We can simplify things a bit. Here we're going to let T be start, S be stride, and E be end. And then given that, we know initially RBX is T. Each time through the loop, we add S, and we compare it to end. So if we go through the loop n times, we will add S times n to T. So we have T plus NS. Now we need that to be equal to E to stop. So we have T plus N times S congruent to E mod 2 to the 64, right? Because we're going to overflow. We could potentially overflow. And we're always in that 64-bit world. So we wind up with that little equation you see on the right-hand side. So we do, in fact, know T, S, and E. If I can find a value of N that makes the above statement true, then the loop halts. If I can't find a value of N that makes that statement true, then the loop doesn't halt. Does that make sense? If there's a finite number of times through the loop such that RBX eventually winds up being the value for end, then we'll fall through that conditional and the loop will stop. But that might not happen. Suppose I pick a start of 0, I pick an end of 3, and I pick a stride of 2. So I'm going to go 0, 2, 4. I missed the end. I go all the way up, I go around, and because there's an even number of 64-bit integers, I wind up right back at 0, and I repeat. And the loop never terminates. So it's possible to always miss the end value and terminate. It might be possible that I missed it the first time, but I go around and I hit it the next time. Suppose I start at 0. I want to hit 1. 1 is my end, and I'm counting by 3. I'm going to immediately miss it. But when I come back around, I'm going to be off by a different number. And each time I go around, I'm off until eventually I hit 1 and terminate. Okay. So if we want to know about termination, we have to ask the question, is there a value of n that satisfies that equation? And if there is, the loop will terminate. And if there's not, the loop won't terminate. Note I'm not asking what the minimum value of n is. I'm asking if there's any value. Okay. To figure that out, we're going to rely on something called satisfiability modulo theories. And to get there, we're going to start by talking about satisfiability. So given a formula, we ask the question, is there a model? And by model, I mean an assignment of values to variables that makes that formula true. If so, the formula is satisfiable. Otherwise, it is not. Now, if it turns out all models make the formula true, the formula is what we call valid. If none make it true, if everything makes it false, then it is a fallacy. Okay. In propositional logic, now by propositional logic I mean we have variables, we have truth constants, we have logical connectives, we don't have quantifiers, no for all or there exists. Satisfiability turns out to be decidable. But in first order predicate logic, where we have for all and there exists, satisfiability is not decidable. And that shouldn't really surprise you, right? The mischief in figuring out properties of programs comes when we widen our aperture to say, here's how you do it for all programs. Then we're in trouble. Right? Same thing here. So let's consider the ones at the bottom. We have not P or P. Not P or P. Well, by the excluded middle, we have to have one of those, and so that statement is true. Note that there are some logics which do allow a middle, and that wouldn't necessarily be true. But there you go. So that one is true. If I assign false to P, then I have true or false, which is true. If I assign true to P, then I have false or true, which is true, and I can only assign true or false, so any assignment of values to variables makes that first formula true, so that first formula is valid. What about the next one? P and not P. Well, if I assign true to P, I have true and false, which is false. If I assign false to P, I have false and true, which is also false. Any assignment of values to variables makes that second one false. It's a fallacy. And how about that last one? Well, if I have P and Q in that, so if I assign true to P and true to Q, it's true. If I assign false to P and true to Q, it's true. If I assign false to P and false to Q, it's true. That's one of the hard ones to think about. If I assign true to P and false to Q, now it's false. So it's contingent, right? So it's satisfiable, but it's contingent. So that first one is satisfiable and also valid. The second one is unsatisfiable and a fallacy. The third one is satisfiable and contingent, neither valid nor a fallacy. Okay, there you go. I hope that all made sense. So, Boolean satisfiability, what we just looked at, turns out to be the first problem proven to be NP complete. It's called the Cook-Levin theorem. Cook was the American who figured this out. Levin was the Soviet who figured it out, and so they both get some credit. Why is that? Suppose I have a sentence that has 1,000 distinct variables in it, each of which can take on the value true or false. I have like 2 to the 1,000 things to check. It's exponential. But once I check them, they're easy, right? I just plug them in and turn the crank and I get an answer. And so it's easy to check, but it's exponential to try to find. That is sort of the definition of NP complete. And so there you go. And if you want to see the paper where that's proven, I've linked it there at the bottom. It's a neat little paper. I kind of recommend it. Well, you can solve these things. There are programs called satisfiability solvers, and they work in a kind of a neat way. First, we see if we can break up the problem into lots of little sub-problems. And to do that, we put an expression in what's known as conjunctive normal form. So that first one, if I just go ahead and apply the distributive property, I distribute the or over the and, I wind up with that second piece where I have 2 atoms that are being ANDed together. That means they both have to be true at the same time. That helps me. You might wonder, how does that help? There's more stuff in that second thing than there was in the first one. That helps because what I'll do is I'll find the solution to that first atom. I'll find a set of assignments, a P and a Q, that might make that first atom true. That's easy. There's just 2 things there. And then I can, if I find one that makes it true, then I check it for all of the other conjoined atoms to see if it makes them true as well. In this case, I have to also pick an R, but I only have 2 choices for that, so I try it with each one of those. And that lets me sort of divide and conquer the problem. It doesn't mean the complexity goes away. The complexity is still very much there. But it lets me break things up and attack it in a little more disciplined way. There can be multiple solutions, many different ways for that to be true. And which one a particular SAT solver chooses can be random, and it can vary from run to run. A lot of them do their work using an amortized cost. So one of the ways, if you've had I suspect you've had a complexity of algorithms class at some point, and one of the ways that you can reduce the actual time for executing one of these is to choose random. So that you try to get close to the average time instead of having the worst case. So there you go. Some SAT solvers like you to specify the seed so you can get repeatable results, the takeaway from this is they'll give you a solution, but not necessarily the solution. And that's important. Remember when we were looking at the termination of that loop, I said if I can find any n that makes it true, then I know it terminates. I didn't necessarily mean find the shortest n. There was n, the n that makes it true, the n that I find that makes it true, might not be the number of times the loop runs, right? The loop's going to run until it hits true for the first time. But all I care about is if it ever hits true. So that's a problem we can solve with SAT solvers. There are lots of these. There's Minisat and Glucose and Ling Ling. And there's also PySat, which is a Python interface to a bunch of different ones, and all the ones above are included. So if you get one of those, you can have a nice uniform interface to them using Python. Well, that's all well and good. But if you remember the thing we were trying to solve earlier, it involved integers, right? I have a start value, I'm adding to it, I'm checking against an end, I'm running a certain number of times. Those are all integer problems, not Booleans as such. So how do I capture that? And that's where satisfiability modulo theories comes in. So let's start with the Boolean satisfiability problem, like the one you see right there in the middle of the slide. And we might go in and replace P with an expression involving something else, in this case an integer. So I replace P with the expression x greater than or equal to 15. So note what happened. I can still run my SAT solver for that first problem, and it tells me, let's say, P has to be false. And so then I ask, okay, P has to be false. So that means, can I find an x that makes that inner statement false? And I can, right? X could be, for example, 7. 7 is not greater than 15. That makes that statement false. So I'm using what are called background theories. In this case, I'm using Pressburger arithmetic. And we can think of it as a tiered satisfiability problem. We solve the outer problem, and that gives us constraints for solving the inner one. We try to solve the inner one. If we can't, we go back and try to find another solution to the outer one and proceed again. Hope that makes sense. Satisfiability modulo these background theories. Some are decidable, like Pressburger arithmetic. Some are not, like piano arithmetic. And there are some that are useful for programming. So now we've worked our way through satisfiability modulo theories. Now let's make it much more concrete. Let's talk about Z3. Z3 is a satisfiability modulo theories solver developed by Microsoft. You can install it with pip, and it has a nice Python interface to it. And if you're on a more modern Linux, you can install it with apt. Some of them will now complain about they want to have very constrained Python installs, and you can do it that way. There's a guide right there that will let you know more about Z3. What does it look like? It looks like what you see over on the right-hand side. Here I've taken our little problem on the left, not P or, not Q and R, and I have directly encoded it into Z3. So I need some Boolean variables. The way I define them is I import bool from Z3, and now I can say P is a Boolean, and I give it a name P. Q is a Boolean named Q. That thing in quotation marks is how Z3 will display excuse me, that variable. And then I create a solver instance, and to that solver I then begin to add the things that we want to prove. And the first one I add is that little guy. So the innermost is not Q, so you see not Q there. And then I wrap that with an and, not Q and R. And then I have a not P, and I wrap all of that with an or. So I can't use the standard connectives for this. They won't work the right way. For the most part, you can use like addition and subtraction and all those good things, and greater than and less than and so forth. But in this case, I need to use these. Then I can check it, so I can see if it's satisfiable. And if it is, I can print out the model, right, the set of assignments that Z3 found. And when I run this, it first tells me, yes, this is satisfiable, and then it tells me false, false, true. Is that true? False, false, true. If you go back, if P is false, then not P is true. True or anything is true, so yeah, that works. Figure that out. Now, I want to point out variables in Z3 are variables in the sense of equations. They're not, you're not going to assign something to them. Z3 is going to try to find a set of assignments that make something satisfiable. So here I've declared some integers. I call them x and y. I get a solver. I add some constraints. I add 3 constraints. I want x plus y to be greater than 8. I want x plus y to be less than 20. And I want twice x plus y to be less than x plus y. That's a little tricky. I then go and see if it's satisfiable. And if it is satisfiable, I print out the results of that. So notice how I access parts of the model that come back. Now, is it satisfiable? Twice x plus y less than x plus y. That seems weird, but that could be true if, for example, x was negative. If I pick the correct negative value for x, then I can satisfy all of those potentially. Okay, you can try that and see. I can also use bit vectors. So computer arithmetic is weird, and so I might want to do something with finite precision. And there's 2 ways to go about doing that, and one of them is to use bit vectors. Now with a bit vector, I can't just declare it by name, I have to tell it how many bits there are. So here I'm declaring an x and a y that are 16 bits wide. And I could also do that with that second line there, which declares x and y, which are both 16 bits wide. And I can define some constants. A, B, C, and D are 0, 100, 4, and 17, respectively, all 16 bits wide. I then define I go and get a solver, and I define the constraints. And notice I'm using the equal, the times, the addition, and the circumflex, or the little caret symbol. And what does that do? You know what that does? What does that do? It's not exponentiation, it's exclusive OR. So I want a plus c times x to be b, and I want x exclusive OR y to be d. So that's a pretty complicated thing to think about, but it turns out that that's fine for Z3. It can go and solve that kind of problem for me and give me back an answer. And so now we're getting into the realm of things that are hard for us to think about, but easy for Z3 to work with. It might also be the case that I can use some modular arithmetic sometimes, right? Sometimes I want to do that. Think of that problem we had earlier where I was computing an n. The number of times through the loop was not constrained by some number of bits, right? My loop stuff could have all been in some finite field, but the maximum number of times I can go through the loop is potentially forever. So maybe it shouldn't be a bit vector. So maybe what I want to do to solve that problem, because the start and the end and the stride are all fixed values, I don't really care about their bit width. And n is a number, an integer, positive integer. So maybe what I want to do instead is use modular arithmetic. Pick the right theories for your problem. And so if you look over on the right hand side, you'll see I've set up a problem where I have a start at 0, a step of 7, my n value is 100, and I create a solver and I say I want to find a v such that start plus step times v mod 256 is equal to the end, right? So mod 256, that's 8 bits. I could have written 2 star star 8 there if I wanted. And so that will do it, right? Because the value that's actually held in the original problem, RBX, but in whatever, is going to be in that finite field, and it's going to be, as we add to it, we're going to do modular arithmetic to it. Now, to point out the, I hope, obvious, modular arithmetic is not the same thing as bit vector arithmetic. It is not the same. So you have to be aware of that when you're picking which one of these you want to do. All right. There's a standard language for SMT solvers called SMT lib, and Z3 uses SMT lib by default. And so you can find guides for SMT lib online. You can find tutorials for Z3 online. SMT lib looks like what you see over on the right-hand side. Now, we've snuck around this for long enough. Can we solve the termination problem with Z3? So, over there on the right-hand side is an SMT lib for solving a version of our earlier termination problem. Here we're trying it with the start equal to 7, the stride equal to 4, and the end equal to 22. If I start at 7, I count by 4, will I reach 22? And the answer is no, and it should be obvious-ish to you after a little bit of thought why the answer is no. It's an even number of 64-bit integers. I'm counting up by an even number, but I'm starting from an odd number. That means every number I reach will be odd. And so I'll never reach 22 because it's even. Hope that makes sense. So I put those assertions in there, and then I try to find an n that, the only one I can vary is n, right? T is equal to 7, S is equal to 4, E is equal to 22, but n is only greater than 0. So that has some wiggle room in it, and it can't find one that satisfies that. All right. Here it is in Python. And notice I've changed the problem a little bit. So I still start at 7, I still count by 4, but now I'm looking for 23. So you can do this in your head, right? 7 plus 4 is 11. 11 plus 4 is 15. 15 plus 4 is 19. 19 plus 4 is 23. Boom. Four iterations of the loop and I'm done. So I plug all this into Z3 and I ask it, and Z3 came back with a value for n, and the value it came back with was 4 quintillion, etc. I'm not going to read the rest of it. So 4 quintillion, that is ridiculous. 4 also works, right? 4 times 4 is 16 plus 7 is 23. I point out that it found a solution. It doesn't have the ability to optimize an objective function, though they're working on that kind of thing. It will tell you if there's a solution. So that's good enough in this case to know that with that was the problem set up that way, the loop does halt. Okay. So, given all that, you can prove termination of programs, right? We just did. Byron Cook created a tool called Terminator to prove termination of programs. Take that, halting theorem. We can reduce lots of problems to termination, right? Once a correct password is entered, the program terminates. Particular strings printed, the program terminates, right? Whenever something that we're interested in happens, we can have the program terminate. And then all we have to do is prove termination. And Terminator tries to find a well-founded relation on variables of interest to prove termination. So suppose, instead of the number of times of the loop, suppose the answer you're looking for, suppose the thing it lets you vary is the password. Then maybe, finding termination means finding the correct password. That's interesting. So there's a YouTube interview with Byron Cook about this, and Terminator I don't think is maintained anymore, but it's now part of something called T2, which you can go read about. And T2 is better than Terminator, right? Because it has the liquid metal robots, and now Schwarzenegger is a good guy. So there you go. This all takes us to symbolic execution. What? It's all going to come together in the next class, trust me. Symbolic execution is just what it says. We're going to symbolically execute a program. Instead of running a program with concrete values, we're going to run it with symbolic values. So over on the right, we see a program. And I could run that with x is 5 and y is 7, and I'd get some output. Or I could run it with x and y. Right? Z becomes twice y. I have a condition, x is either equal to 100,000 or it's not, etc. So I can observe its behavior for concrete values if I have proper experimental controls, right? Modulo timing and scheduling. If I just run that program and I try different values of x and y at random, and I don't know anything about what's going on inside it, it's a black box to me, how long will it take testing to find that? Suppose that were a bug. How long would it take random testing to find that bug? Well, there are 2 to the 32 int values, right? Only one of them is 100,000. So I have a 1 in 2 to the 32 chance of picking an x that triggers that inner if. But even if I do, I've got to pick a y such that x and z trigger that innermost if. So they're about 2 to the 31st minus the 100,000 values for y that will work because of overflow. And that's small with respect to 2 to the 31st, so I can approximate it with 0 and say about half the values may satisfy the inner predicate. And that adds another power of 2, so now I'm up to 2 to the 33. That's about 1 in 8 times 10 to the 9th. I'm not going to find it by random testing. It's very unlikely. But I can potentially get there with path coverage. Path coverage is much better. So how would I do that? I can convert it to static single assignment, use back substitution to figure out predicates. That's pretty easy. You can try it. There's not much going on because nothing gets updated, so it's super easy, and you wind up with 3 conditions. X is 100,000 and x is less than twice y. X is 100,000 and x is greater than or equal to twice y. X is not 100,000. There you go. I could use a tool like Z3 to generate specific cases for each of these, and there's how I might do it. So I set x and y to be ints. I set S to be a solver. I add some constraints to it. I check it. It gives me back a model, and there's one potential model. Y is 50,001. X is 100,000. And that will work. So, for example, the first thing I do is set Z equal to twice Y. That would be twice 50,001, which is 100,002. X is in fact 100,000, and 100,000 is less than 100,002, so that innermost thing triggers. I can get concrete values that cover each of the paths. But for a large program, path coverage gets problematic. Now, symbolic execution refers to running the program on symbolic values. And what we would do is we would basically have a symbolic value, we'd plug that into the semantics of whatever instruction we're looking at, and then we'd use a tool like mod or cock to simplify that, and we'd just walk through the program that way. You did trace tables earlier. That's kind of a form of symbolic execution. The challenge with symbolic execution is that it builds a tree structure. And the tree structure can become very, very, very wide, very complicated. Paths can explode. Now, for the program over on right, that's not so bad. We have an outermost predicate. That's a branch. We have an innermost predicate. That's another branch. It's not too bad. For that one, we wind up with a tree that looks like what you see over on the left. That tiny program gave me those 6 nodes. There's more nodes than there are lines of code. There are only 5 effective lines of code in that program. There are 6 nodes over there. For a real program, that tree is going to be ridiculous. Ridiculous. So, we're not going to want that. It is worth noting that I can derive conditions for different areas. that asserts 0, I just follow the path down, right? Z1 is twice Y0, X0 is going to be 100,000, X0 is less than Z sub 1, and I can combine those. I can do bad substitution, and I can figure out that Y has to be greater than 50,000 for that to trigger. So I can do all those kinds of things. Right? Does that make sense? Notice from the above, I wound up with that one condition. And we could ask the question, is that true? And the answer is it's almost true. We have to take into account 2's complement arithmetic. A large enough value of Y multiplied by 2 might also work, right? Or a very large negative value of Y multiplied by 2 might overflow and give us a weirdly positive value. Strange things happen. All right. And we point that out here. I take that crazy int value right there, I multiply by 2, and I get 100,002, which works. That's horrifying. All right. It's important to use a term rewriter or theorem prover that understands this. One of the reasons we couldn't use mod for an earlier project, mod didn't understand that. I don't know about it today. That was over 10 years ago. It's important that you have one that understands this bit vector manipulation. Suppose you already knew about the error. Suppose you just wanted to generate an input that reached that error. Well, symbolic execution is powerful. They can tell you about any execution of the program. And concrete execution is simple, but it can only tell you about a specific execution. We could combine the two. We could do concrete execution to figure out what actually happens, and symbolic execution to figure out what path we take. That would be kind of neat. We do that. It's called concolic execution. Concolic is a little neologism. It combines symbolic and concrete. Right? It's concrete and symbolic. It's concolic. That's it. We'll resume with this next time. Take care.